Consider this scenario. You are asked to do an experiment to determine the coefficient of linear expansion for a steel rod with an initial length of 103.45 millimeters at 20 degrees Celsius, or basically room temperature. Here is the steel rod, and I can take a measurement of this using a vernier caliper. And I've done that. I've measured this little length of steel and here between here with the vernier caliper. And in this case right now I'm getting about 43, there it is, 45. So on average 103.45 millimeters at 20 degrees Celsius for this scenario. And it says here, you place the steel rod in a heated tube with a dial indicator at one end, allowing you to measure the increase or the decrease in length. Now, all materials will either increase in length or decrease in length depending on temperature. If you heat something up, it gets longer. If you cool something down, it will get shorter, so increase or decrease in length. After heating the rod to 90 degrees Celsius and allowing a few minutes for stabilization, you read the dial indicator and it reads plus 0.085 millimeters. And the question is, find the coefficient of linear expansion alpha, and then compare this alpha to accepted values of alpha that is in the literature. Well, let's draw a little sketch of what all of this means. We have a tube. Here is a tube. I'll just do a side view of the tube. Here's the tube. And it's circular in cross section. It looks something like this. Ooh, steel wall. If I look at it from the side, look at it from the side, it has circular cross section. And inside of this steel tube is the rod. And I'm just going to put a stop here, and I'm going to place the steel rod inside of this tube and have it protruding a little bit as well. So there's the steel rod inside of this tube. And we're going to put a dial indicator right here at the end. Is going to be a dial indicator. Here's the dial indicator itself. And it has a little stem, and that stem generally extends out to the other side so we can lift it up and put it back into place. And there is an arrow on the inside, and this will rotate. Generally it rotates clockwise for showing an increase. And we're going to zero the dial indicator with this position right here. We'll call that 0. And the tube itself, it has some means of measuring temperature. So we'll put in a temperature readout. Some means, whatever a particular library or laboratory might want to use. So some kind of temperature readout. And we're going to start at 20 degrees Celsius. And then this tube is going to get heated. There are means of heating this tube. So we put an inlet here, say of steam, or you can have coils, many different ways of heating this. And have an outlet here. If you're going to have steam going in, we'll put an outlet out here. So it's that the temperature here is going to rise to 90 degrees per our scenario. And as the temperature rises, well, the steel that we have in here is going to expand lengthwise. It'll expand in all directions, but mostly in lengthwise. This is where most of the material lies along its length. As it expands lengthwise, this arm to this needle here is going to be pushed up, and the needle in the dial indicator is going to start to rotate. And it will rotate here. And let's say it goes this far, and this reading is going to be plus 0.085, plus 0.085 millimeters. So at 90 degrees Celsius, this rod will have expanded this amount, or grown in length by this amount. Having explained all of this, let's have a look at the equation for change in length. Change in length is written delta L is equal to alpha. This is the coefficient of linear expansion, which we are asked to find. times L naught, change in temperature. What we have written here is the general equation. Now let's look at these two terms. Delta L. That triangle is the Greek letter delta. And L, they represent length. And delta means change in whatever the unit is. In this case right here, it's going to be length. So the change in length. And it's simply shortened to delta L, and it's understood it's going to be a change in length. And this is a subtraction. Some kind of a subtraction is going to occur here, or subtraction. That's what that delta means. A subtraction has occurred. And we look at delta T, it's the same thing. Delta T. That's the triangle delta. And T represents temperature, so this is the change in temperature. Change in temperature. Again, this will be a subtraction. If this is the general equation, well, let's expand these two, delta L and delta T, to see what it looks like. In the expanded form, delta L, the subtraction itself, it looks like this. It's the length final, the final length minus the initial length. Minus initial length. This is delta L is equal to alpha. L naught is the original length of the bar. In our case right here, the original length of this before being heated. We said it was going to be 103.45. This is L naught. L sub naught. That 0 or naught, it's Old English representing the number 0. Pronounced L naught, and it means the original length, the initial length, times delta T, and delta T is temperature final minus temperature initial. This is the working equation. Where the deltas are all expanded. So we can do a final length, we can measure an initial length, we can measure the final temperature, we can measure the initial temperatures and put all the numbers in here. In the shortened version of this equation, it looks like that. The working version looks like this. In our case, we're actually measuring the length itself. So length final minus length initial is being given to us right here. This dial indicator is doing the work for us. So that delta L is 0.085. Another way I can do this, I know what the original length is. I can add that much to it. Then I know what the final length is, and I take the final minus the original, and I'll get this value. So this is delta L, given to me by the dial indicator. That already is change in length. Since I already have this, I can rewrite this equation as such. Change in length is equal to alpha L naught temperature final minus temperature initial. Now the question asks us to find the coefficient of linear expansion alpha. So we're going to take this equation, rearrange it to isolate alpha, dividing both sides by L naught and temperature final minus temperature initial. Bringing it to the left-hand side, it will look like this. Change in length, divided by, we're going to divide by L naught, and temperature final minus temperature initial is equal to alpha. Putting in the numbers now, equals, and I'm going to put it on this side. So alpha is equal to the change in length. Well, we determine the change in length by this dial indicator. 0.085 millimeters divided by L naught, the original length. The original length we measured to be 103.45 in millimeters. 3.45 millimeters. And the temperature final, we brought this to 90 degrees. Temperature final then was 90 degrees. Minus the temperature initial. In the temperature initial, we started at 20 degrees Celsius. So we have everything we need. Just a matter of putting these values here into a calculator to calculate alpha. And let's do that. Here we go. Oh, let's look at the units. Millimeters and millimeters cancel out. And what's left over is degrees Celsius. And it's in the denominator. So let me do one more step here. The millimeters are canceled out, so the equation looks like this, 0.085 divided by 103.45. And 90 minus 20 is 70 degrees Celsius. So the unit is going to be per degrees Celsius. It's in the denominator. So let's do this calculation in our calculator. 0.085 and divided by 103.45 equals, and divide that by 70 equals. And I'm going to change that. Here's my value for alpha, 0.00. I'm going to write that down. 0.000011738. And the units left over, it's degrees Celsius in the denominator, per degree Celsius. So let's clean this up here into scientific notation. So we have here, let's go to 1, 2, 3, 4, 5. Let's go to 6. And I'm only doing this in order to compare to the textbook value. Otherwise, I would normally go to 5 minus 5 for decimal places. But let's go to 6 minus 1. So the decimal could be 1, 2, 3, 4, 5, 6. 11.738 times 10 to the power minus 6 per degree Celsius. And the final thing we need to do is to round this value here into proper significant figures. And here we have 1, 2, 3, 4, 5 sig figs, and this one is 2 sig figs, and this one is 2 sig figs. So we'll go round this to 2 sig figs, so alpha. Coefficient of linear expansion approximately equal to, rounding that to 2 sig figs. Look at that third. This goes up 1. 12 times 10 to the power of minus 6 per degree Celsius. And finally, it says here, compare your findings to an accepted value of alpha. And this would come from a textbook. A trusted source. So let's do that. Let's have a look at this in a textbook. And here is a physics textbook. I just have to clean up my desk a little bit so I can fit this in. Let's see. There's the textbook. Can't see it all. Physics textbook. It says physics here somewhere. There we go. Anyways, going to coefficients of linear expansion. Here's the chart. And we can see here aluminum has a value of, and I'm going to move these down a little bit, 23 times 10 to the minus 6 per degrees Celsius. This says Celsius degree, but that's a comment for another video. We'll just simply say what degrees Celsius. And brass, here's the coefficient of linear expansion for brass, concrete, copper, and we want steel. And here is steel. Of course, it's a rounded version, just like I have shown you here. So it's been rounded to 2 sig figs at 12 times 10 to the minus 6 per degrees Celsius to the minus 1. And nickel and sulfur, and there's some And then there's some volumes here. These are all the solids. And here is the equation we worked with right here. And here we have it. Calculation for alpha for our scenario given this information that we have here.